45 seconds. We're going to go over a couple of problems together, and then it's going to be whiteboards. And also we'll just finish off the notes for chapter, whatever this is, 2.3. So if you're already in the warm-up, go ahead and start putting in the notes. Review of position, velocity, throw, and acceleration. We have a summary here of all this stuff. There's a little distinction between speed and velocity. They're not exactly the same. They're related to each other, but speed is just how fast you're going, and velocity is how fast and in what direction you're going. And if you're curious what the derivative of acceleration is called, we're not going to really talk about it, but it's that. If you're still working on the warm-up, you got another 15 seconds. Like what I do every day?
No, like for like AP physics, it's like let's say that like variable function, you have like something equals b and then the function over dx, and it's like
you then go through the process that you learn here.
You have to like write any like symbols and stuff.
Nah, you just do the derivative. So if you're using your quotient rule or your product rule, you just use it. If you just use power rule, you just use it. It's a trig function. Just what's the derivative of cosine? Oh, it's negative sine. Plunk. You don't have to do like any fancy notation. If you can show me like specifically an example, that might be helpful, because I think you're overthinking it.
Your brother explain a lot of things.
Sometimes the brother explains things.
No, you should know this already.
Yeah, he's assuming that you're in the AP class. Should have taken this class last. All right, go ahead and hand in your warm up. Friends, how many of the people in your physics class are in the same boat of not having had or not being in Cal? Also you? Also, you're also in my brother's class? Okay.
Like 4 or 5 people are like hard in calculus. Like a third of the class, 2/3 of the class.
Ooh. Rough. And they should go together. Like if you're in AP Calc, you should be in AP Physics and vice versa, because they reinforce each other so well. Anyway, so I don't have space here, so I'll do it over here. Position, we want to find the position at time equals 9, so we'll just plug 9 directly into the function we have. Lucas, could you please turn the light back on? So S of 9 would be 3 times, thank you, 9 squared minus 8 times 9 to the 3 halves. 9 squared is 81, times 3 is 243. That's 27. What's 27 times 8? What is it? 215, 216, thanks. And then that is 27. So your position is 27. That's where you are, because that's positive. You're on the right side of your number line. So if you imagine a number line, here's your origin, here's 27. You're on the right side, because that's a positive 27. That's where you are right now. So put a dot there to represent where you are. Then velocity is the derivative of position. So we could say V is S prime, and that's going to be 6t minus 12t to the 1/2. And then plug in 9 to this to get your velocity at that time. So you have 6 times 9 minus 12 times 9 to the 1/2. 6 times 9 is 54. That's about 5. 6 times 9 is 54. 9 to the 1/2 is 3. 3 times 12 is 36. 54 minus 36 is 18. So that's your velocity. That's not another point on the number line. The number line tells you where you are. Velocity tells you where you're going and how fast. Because your velocity is positive, in what direction are you moving? To the left or to the right? To the right, because that's positive velocity. You move in a positive direction, and that's to the right. So that gives us like an arrow here. All right, we arrow to the right, and it just tells us we're going at a speed of 18, whatever, miles per hour. So since we're moving to the right, and we're already on the right, how are we moving relative to the origin? Are we getting closer or farther away from the origin? Farther away, so we're moving away from the origin. So that's part two. If velocity and position are both positive, or if they're both negative, you're moving away from the origin. If they have opposite signs, if one is positive and the other is negative, then you're moving towards the origin because they're like fighting against each other. Yes, sir.
So I don't know if it's like a particle is not going to like start moving.
Well, it could, but at this moment, it's moving in a positive direction. In the future, maybe it'll slow down, stop, turn around, start moving back to the left. Like at time equals 1, 6 minus 12 equals negative 6. So at time equals 1, this is moving in a negative direction. And then at some point, it changed direction and started moving to the right. So there was a moment between time equals 1 and time equals 9 where the velocity was 0, and it was at that moment standing still because it was in the middle of changing direction. So that's going to be that's like a chapter 3 sort of question. And so, given enough time, we'll get there. Ryan.
You have a negative velocity here. Negative position, positive velocity.
Yeah. So a negative position just means you're over here on the left. So if you were at a location of like negative 20, you have a negative position. You're just over here on the left side of the origin. You could be over here, but be moving towards the right. And then you would have a negative position, but a positive velocity. So a positive velocity just means you're moving to the right. Think of like up, down. Like we have nuclear silos in this country, right? And all the nukes are underground, or we have nuclear submarines and those are under the water. So those positions are negative, right? Now, if God forbid we launch one of those things, it's launching up. So we have a negative position, but a positive velocity. We're underground or under the water, but the missile's going up. And then eventually it'll unfortunately come back down. And then we have a mess. But that would be an example of like we have a negative position and a positive velocity. So that would be you're under the ground and then you're moving up towards the origin. So yeah, anytime position and velocity don't agree with each other, anytime one is positive and the other is negative or vice versa, then that's a situation where you're moving towards the origin. Because if you have a positive position, but your velocity is negative, now you're over here on the right, but you're moving towards the left. Any other questions? All right. Now, the relationship of position and velocity. Velocity is the derivative of position. Throw acceleration in there, and that's just the derivative of velocity. So acceleration tells you how does the velocity change over time. And since velocity was already the derivative of position, we can say that the acceleration is the second derivative of position. So we have this new idea of a second derivative. You could go to a third derivative and a fourth derivative if you wanted to, but mostly we don't. Mostly we stop at a second derivative because that's kind of the limit of what we can wrap our heads around and do usefully. There is such a thing as the derivative of acceleration, and it's called lurch or like jolt, and that's how the acceleration changes. But we're not going to really worry about that. So if you're ever told, hey, find the second derivative of position, that's what the acceleration is. And if you're ever asked about speed, speed and velocity are not quite the same thing. Speed is just how fast you're going, and we don't care where. We're just going 4 miles per hour. You could be going 4 miles per hour to the left or 4 miles per hour to the right. Your speed is 4. Whereas velocity, if you're moving to the left, we want to make it negative. Or to the right, we want to make it positive. So velocity, you care about where you're going as well as how fast. Does anybody need more time with those things? Yeah. All right. And then we're going to add on to this just a little bit more notation with, okay, what does second derivative and potentially third and fourth derivative look like in terms of the, like, how do you express that with notation? No, the other remote. Oh, it's hiding over there. Lucas, can you turn the light back off, please? Is it okay if I scroll, Rachel? Yeah. All right. So here is the rest of the notes for chapter 2.3. These other derivatives, second, third, fourth, and so on, are called higher order derivatives. And depending on whether you're using y or f prime or dy dx notation, how you express that looks a little bit different. If you're just using y and f notation, you just add another like apostrophe looking thing for a second or a third derivative. Eventually, you don't want to just keep adding extra tick marks, so you don't want to have y quadruple prime. So you put like the little y and then 4 in parentheses. And because it's 4 in parentheses, it's not an exponent, it's how many derivatives you've taken. But for first, second, and third derivative, you just put the little apostrophe things to indicate which derivative you're at. For the dy dx notation, it looks like this. And then these things over here, the last two columns I wouldn't really ever worry about. In my 2 years of teaching AP Calc, I haven't run across this notation hardly ever, and I've really never seen this. So that's just in the textbook as like a curiosity from the past, I guess. So the first three columns you got to recognize for what they are. Keep adding a tick mark until you get to the fourth derivative, and then if you see the number in parentheses, that's indicating not an exponent, it's that level of derivative.
So the first line, the fourth column.
First line, fourth column.
Yeah.
So when you see this in physics,
Yeah,
right?
So, so instead of f of x, let's say it was like 4x.
Yeah.
And like the derivative of 4x is 4.
So you write equals 4. Right? So you would just write equals 4. So if you have EDX, put a function in there. You said call it 4x. The derivative of 4x is 4, so you'd say that equals 4. Done.
And we would have like e big volume is here. So like e equals
Volume is 4 first pi r cubed.
what is the d from the d?
So it's just the rate of change of the volume. So wouldn't there be like a dr over here? Maybe. Yes. Hard to say. Yes. Yes. How many do you agree? Okay, cool. So then what?
So then like how do you show off? Like you are like on the steps after that.
So if you want to like then take the derivative of this, you have 4 pi r squared dr.
Why did you
Are we taking the derivative with respect to time? Because then you would get a dr dt. And this would be a rate of change of the volume over some time period. Time is weird because you don't see it, but it has its effect on things. We'll talk about time when we get to end of chapter 2. So like that's the last thing in chapter 2. We're going to do chapter 2.1 to 2.5, have a unit test on chapter 2, and then we'll have a separate mini unit just on 2.6 where we get introduced to this stuff. That's called related rates. Close on. Yes. How would you write for the third column? You have like, instead of y prime equals whatever the derivative is, you'd say dy dx equals whatever the derivative is. So we'll use this notation more in 2.5 when we start talking about implicit differentiation. For right now, we're mostly using just these two columns. This column will show up more later on in the chapter, and these columns show up almost never unless apparently you're business.
For the third column, is there like something next to the x?
That's dy over dx.
Yeah.
That's d squared y over dx squared. There's d cubed y over dx to the third.
Is there like something next to the numbers?
Oh, that's a comma separated from the next column. So then that's d fourth y over dx to the fourth, and so on.
Thank you.
Yep. Any other comments or clarifications we want? Okay. You guys done with that? So in terms of like doing examples with this velocity and second and third derivative stuff, we're probably going to hold off on that until tomorrow. And today is going to be mainly do another example or two, see how do we use a graph to find a derivative, and in combination with product or quotient rule, and then give you guys a chance to do just practice using quotient rule and product rule on your whiteboards. Lucas, could you turn the light back on, please? Thanks. All right. So yesterday we finished here. How much of this did we do? I can't remember. Nothing. It was up here. So again, could we do quotient rule? Yeah, absolutely. Do we have to? We don't have to. Now we broke it down. So to avoid quotient rule, if you looked at that and say, I don't think I have to do quotient rule, I would prefer not to. 1 minus cosine x all divided by sine could be rewritten as what? And then what is 1 over sine x the same as? That's cosecant. And what's cosine over sine the same as? Cotangent. And then you could say, well, I could either just use my trig derivatives for cosecant and cotangent, or I could stay here and do quotient rule. So we'll do both methods, and you can kind of see how, depending on the pathway you take, you might have different looking answers. It doesn't necessarily mean you're wrong. It just means you took a different pathway than somebody else, which is useful for remembering when you go to look at the answer key and you're checking your work. You might have done something a little bit different than I did, or maybe I took it farther on the key than you did, and it doesn't necessarily mean you're wrong. It doesn't. You might be wrong, but it could just be, oh, you did it a slightly different way, or you didn't simplify as much as I did, or you didn't do a trig identity that I did. So if you just now take the derivative here, what's the derivative of cosecant? The negative cosecant x and cotangent x. And what's the derivative of cotangent? What is it? Negative cosecant squared x. And then we're subtracting the negative here, so we could say that's a plus cosecant squared x. And I suppose if you wanted to, you could factor out a common factor of like negative cosecant, and you'd be left with cotangent x minus cosecant x. But I don't really care if you do that or not. Both of those are totally fine. So that's one way of expressing your derivative. And that's non-quotient. So if your denominator is just a single term, you can potentially divide that out and avoid quotient rule. But if you don't know your trig derivatives for cosecant and cotangent because you decided, yeah, I'm not going to memorize them, and then you look at that and say, oh, I guess I can't differentiate that, then you're stuck back over here and you have to do quotient rule after all. So for quotient rule, let's see what this looks like. How does quotient rule start the numerator? Low d high, so what's low? Sine x, and what's d high? Sine x again, right? Because d high, that's 0, and derivative of cosine is negative sine, so derivative of negative cosine is positive sine, so we have sine times sine, minus what? pi, 1 minus cosine x times cosine x, that's d low, all over sine x all squared, low. Then you go through and you clean this up. So what's our numerator going to look like when we distribute? Sine squared x minus it's a weak word point, but a mistake is a mistake. There you go. Thank you, Zelda. All right, sine squared x minus what? Tell me. Distribute.
Cosine minus
Be quiet. You. So don't listen to Prince. So minus cosine x, and then what kind of cosine squared? Plus, because minus minus is plus. Careful with your negatives. Then, can you simplify this at all? Yeah. It's hiding, but there's a trig identity that you can do on top to really make the numerator a lot nicer. You have a sine squared, and what pairs nicely with sine squared? Cosine squared. And they're both positive, which means they really do pair nicely. What's sine squared? Ignore this guy. Plus cosine squared. Why do you ignore them? What's 3 minus x plus 1?
No, why? How?
How? By just not looking at it. So, seriously, what's 3 minus x plus 1? What does that make? 4 minus x, right? So you ignored this guy and said, these guys can go together and make 4, so that's 4 minus x. So in the same way, these guys can go together and make 1, and you have 1 minus cosine x. So you momentarily ignore the cosine x. You're like, you don't fit in with these guys. They'll get together. And you're left out in the cold being a minus cosine x. Nobody likes you. And that's over sine squared x. So, ta-da! Now, could you simplify this some more? Yeah, in a variety of ways. You could divide everybody by sine squared. No. Or you could turn sine squared into 1 minus cosine squared with a trig identity, and then factor that, and you'd be left with 1 over 1 plus cosine x, but you don't need to worry about that. This is fine, and you can see that this looks significantly different from this. But you could get it to look like the top option if you divided out the sine squared. But you don't need to. So depending on how you go and how far you take things and whether you want to divide out or whether you want to rewrite the denominator with another trig identity and then factor it and then cancel and reduce the fraction, your answer is going to look pretty different. So this could also look like 1 over 1 plus cosine x if you wanted to, but probably you don't, because that's good. So any comments with example 9 to follow that up?
So could you divide out the sign and then get minus cosine?
Which signs?
Right above
Here? So you could divide those and say we have 1 minus cosine x plus cosine squared x, but this stuff would still be over sine squared. So you could say this is 1 minus cosine x plus cosine squared x over sine squared x. Maybe make this a 1 plus negative there. So it's not just this sine squared that's getting divided by the sine squared in the bottom. All of this stuff is getting divided by sine squared. So if you divide these out and make that 1, you have to also remember these cosine things are also getting divided by the sine squared. They don't like turn into their own separate like whole number thing. So it wouldn't just be 1 minus cosine x plus cosine squared, you're done. These things would have to still be over sine squared.
How do you know what?
That's a good question. That's another like, oh man, I wish you guys had had like pre-calc in a venue that allowed for like really doing trig identity proofs. Because with trig identity proofs, you have like a natural stopping point, and you kind of get used to that. Who actually did trig identity proofs in like for real? And mostly like meh, because it was virtual. So how do you know when to stop? when you don't have like a trig identity like reaching out and punching you in the face, like this should reach out and say, hey, make this 1, and then please do that. But at this point, it's no longer like an obvious simplification. So this would be a reasonable place to stop. You could keep going, but if you keep going farther enough, you could end up like in a vicious cycle where you just go in circles and like this simplifies to that, this simplifies to this, and then that takes you back to where you started with, and that's also useless. So there's a little bit of subjectivity in terms of like where you choose to stop. But if you see a sine squared plus a cosine squared, please make that 1. Or if you see like a sine over cosine, and I'd like, oh, it's sine over cosine, period. Just make it tan. All right. One other example up here where we say, hey, let's look at a graph and use a graph to find derivatives. Nope, I didn't want to do that. Back on. And this thing, I'm looking at, where did it go? There it is. Lucas, could you kill the light again, please? Thanks. So here we've got a graph of f and of g. Can you see them okay? All right. We've got 2 functions. We're going to call p f times g, and then we'll also call q f divided by g for a product and quotient. And we want to find the derivative of p at 4, and then the derivative of q at 7. So first of all, before you start trying to evaluate p prime of 4 specifically, you want to say, well, I'm doing p prime, and p is defined as being f times g. So what rule do I need to use to get p prime in the first place? Product rule. So you would come over here, and you would say, let's get p prime of x in terms of f and g, just doing the product rule on f times g. And then we'll kind of come back to the graph and figure out, well, what's going on at 4 with all of these things anyway. So product rule tells me I should have what? First times derivative of the second. First is f. Derivative of the second is g prime. And then plus second times the derivative of the first. So the derivative of the first is f prime, the second is g. Or if you called it g times f prime, same thing. So then we want p prime of 4 specifically. So we're just going to go through here and log in 4 to all of these functions. So f of 4 times g prime of 4 plus f prime of 4 times g of 4. And then we go over onto the graph and find all of these things. So f is the height of the curve at 4, and f prime is the slope of the curve at 4. Because f is just y, and f prime is your slope. So remember, derivatives are slopes, so when you go to find the derivative, you're finding the slope at that point. So we come over onto the graph, and we're trying to find f of 4, first of all. So we find our f curve, found them, and we go to x equals 4, here he is, and what's f of 4? 1. So you come over here and you put 1. Yeah. Then you do the same sort of thing with g prime. So you find g prime, or you find g, found him, and you go to 4. And here, for g prime, we're not finding the height of the curve, we're finding the slope of the curve. What's the slope of the curve here right at 4? 0, because the curve there is flat. So you could say m equals 0. So we'd say g prime of 4 is 0. 0. And then f prime, you go back to your f curve at 4, and now we're doing the slope of f. So what's the slope of this f curve at 4? And since this is a line, it's the slope of this whole section. So that's 1/2, right? Up 1 over 2, up 1 over 2. So the slope of that line section is 1/2. So the slope right at 4 is 1/2. Oops. Did I make a mistake, Joanne? Is that reading correctly now? Yeah, oops. Yeah, that should be g of 4. Sorry about that. And then g of 4 is go onto your curve and find the height of the curve for G at 4, which is 8. So G of 4 is 8. And this is what we have. So F of 4 is 1, G prime of 4 is 0, because the curve there was flat, so the slope was 0. F prime of 4 is 1/2, because the slope of F is 1/2, x equals 4, and G of 4 is 8, that's the height of the G curve. And then you do that, and you get 0 plus 4 is equal to 4. So P prime of 4 is 4, ta-da! Go. So on your homework, not tonight, but tomorrow night, you'll have another problem along these lines where we give you a graph, and we tell you we got an f and a g function on the graph, and then define p and q as product or quotient, and then you're using your product rule to figure out p prime generally, and then you go to a particular number on the graph for x and figure out the height of the curves and the slope of the curves at that point. So what I want you guys to do right now is try number B for yourself for q. So figure out q prime of x over here, the q prime of x, get an equation for that in terms of f and g using your quotient rule, and then go into the graph and figure out where things are when x is 7. So at that intersection point. And this can be a whiteboard problem, right? So, or in your notes, I don't care. So go ahead, try that for yourself and see how you do with it. This is a Q. This is a G. Q is F divided by G, same as if P was F times G. Yes. So if you had a vertical asymptote, then the derivative would be undefined for that function, and you'd break the whole thing. So then the derivative overall would be this. Because if the derivative doesn't work for one of these two functions, then I think that would necessarily mean that the derivative for the whole thing doesn't work. Yes. I think you messed up your signs in your numerator. So go back and check minusing, and also what's the slope of G? Positive. That's good, Sahil. Slope of G, what direction is G going? Yeah, so. You did run up the rise. So F is going up to it. Slope of F is 2. on and F prime for this section. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Let's load that. See, same step. So F prime, rise over run, going up 2 over 1, not up 2. You fix it. Good. So here's minus 6. So that's good. Minus that over my. Now you gotta go into the graph. Now you gotta get into the graph. It is. So I think you're doing this backwards. So you're doing low. Overall function is Q. So low time on time. That's good. Yeah. And then this is good. And then you reverse it. So Q is up to 4. F prime is this guy's slope, not this guy's slope. So this is 2 over 1. And then minus this guy's slope. And that's going down. Think about what that does for slope. You also need to be able to read the graph, so I would recommend you extract that information from the graph and then actually do. Alright, so slope F. You're saying slope F. F is going up 1, up 2. The slope of F is 2. Alright, so mostly we're running into issues with doing the quotient rule backwards in the numerator. Saw that a little bit, but mostly not. A bigger issue is misreading F when we get the slope of F and doing the slope of F as 1/2 instead of 2. So you're going up 2 and over 1, so this slope should be 2, not 1/2. And then the other issue is that some people are forgetting that G is going down, so his slope is -1, not +1. So when you go to do your derivative, you would have low is G. So G of 7 times F prime of 7, that's low D high, minus high is F of 7. D low is G prime of 7. And then low is G of 7 all squared. And then G of 7, G is at a height of 4. F prime is 2 because the slope of F is 2. Minus F is at a height of 4. G prime has a slope of -1. So G prime of 7 is -1. And G of 7 is 4, and that's getting squared. So that would be your setup with actual numbers when you extract information from the graph. And then you have 8 plus 4 is 12 over 16 reduces to 3/4. So that's what that should look like in the end. Do you guys have any follow-up comments on that? So tomorrow night, not tonight, but tomorrow night when you have your homework and you have this guy, and you're doing basically the same thing except at different values, because it's a different graph. You've seen an example of how this works. But we're going to move on and just do some whiteboard practice. So that can go away. And Lucas, last time, could you please turn the light back on? Thank you. You've gotten really good at that. Yeah, still on the whiteboards. So what? Yeah. h of x equals 3 minus 1 over x over 2 plus x. Go ahead and find h prime. I recommend you don't jump right into the quotient rule. You will have to use quotient rule, but I recommend you clean this up a little bit before you jump in and take the derivative. Leave the denominator alone. Don't shoot that out. And so why do more work when it's going to leave it alone? And then in the numerator, you have some sign errors. So when you distribute, you have to distribute the negative of the minus sign. And that's going to combine with negative 1. So you got to put some sign. Otherwise, that is mostly good.
I don't want to.
Everything else is good.
I don't want to.
So you can get things the hard way. Jump right in. Whatever you hide, the I is going to be your way. 1 over x squared. I low. So you have a plus 1. Parentheses, that should be a 1 over x squared. That's going to affect the I. And I would shoot out as normal as what you did, but that's slightly here. Everything else is fine. You'll just have another game. I would recommend you multiply by x. That's good. That's a 2 out front with a 6. You're missing a minus 3x squared in the numerator. Because when you distribute at the beginning, that makes sense.
I know it's tricky.
Well, I don't want to distribute it.
Rachel, that's cool.
Thank you.
Yes. Yes. You can check it.
H prime of x.
All your signs in the numerator are opposite. So I think you did your quotient rule backwards. That'll usually produce that result. All right. So if you jump right into quotient rule right off the bat, then you're doing the Kaza method, and it can work, but then you're going to have a very messy looking answer with negative exponents all over the place, and it's annoying. So to avoid having to fight with negative exponents, multiply by fancy 1 right off the bat, and that'll give us 3x minus 1 in the numerator, and then 2x plus x squared in the denominator. And then do your quotient rule, and it's going to be so much nicer. Looking at your work, mostly good stuff, just some carelessness with distribution and with negative signs, or with setting up the quotient rule backwards so that everything is opposite from what it should be in the numerator. But if you're careful with distribution and keeping track of little details with like exponents and negative signs and multiplying things correctly, then you'll be fine. What's wrong with this? That's fine. All right, another one. F of x equals 3 square root of x cosine x.
What is that?
Good. No, I got the thing. Because I do it backwards from my notes, so which means I'm doing it backwards from all. But yes, yes, and because it's product rule and we're just adding things, it doesn't matter the order. But it certainly makes this part. Yes. Yeah, because you're like 3 plus 4 and 4 plus 3 are the same thing. You can just rearrange the order of the product rule in a way that you can't close. And then you went ahead and got them together. So like, that's cool. That's cool. You got them together and then factored out 3. Negative 3. So cut back in.
I don't know if it's
Yeah, that works. Yes.
You put that wrong.
Wrong.
0 out of 0.
Keep the x to 1 half out front. So it's just sign of x, and then have another x to 1 half out front. Otherwise, you're fine.
But I got
Go ahead and multiply.
well, he has an x equal 1 to
Otherwise, that's good. You did similar thing to.
Oh, I did. I drove in from.
This is your fault. Okay, throw X down the stairs and multiply these so you have minus 3. You can stop right here. You went and got things together. I like things to be as special. Yeah, that's good. So that you just got a common denominator. So you have
Sword, I didn't steal it.
So this kind of goes to Lucas's question earlier of how do you know when to stop? Well, where you stop and where you stop and where you stop might be different. So I saw like Chris and Lucas were comparing notes, and there was like, what the hell? It's completely different. No, but you were both right. So not low D high. Derivative of the first is 3 over 2 root x times the original second plus original first times the derivative of the second, and you end up with 3 over 2 root x cosine x minus 3 root x sine x. And you can go ahead and stop right here, and that's fine with me. Most of you, I think, did it the opposite direction and have this thing going first. So you had minus 3 root x sine x plus 3 over 2 root x cosine x, and that's fine. Some of you went and got a common denominator of 2 root x. So you multiply it over here by 2 root x and turn this into 6x sine x over 2 root x to combine with this first piece so that you can get them together into a single fraction. So I saw a little bit of this, which is great. And then a couple of you went one step further and took out the 3 you see as a GCF, which is also fine. So if you stopped here and your neighbor stopped here or afterwards with a GCF out front, you'd be looking at things as they don't look the same, but they are. It's like I could call you Ryan or Mr. Corici. You're the same person. Let's do another one. When are we out of here? Never mind. Let's not do another one. Let's get on with it. So continue. Hopefully you already started your homework, but continue your homework tonight. It's due tomorrow, 2.3b. Yo. I